All right, so let's talk about stars. Stars are an interesting phenomenon because they have nuclear fusion going on in their core. Right? We didn't really understand that until the 1920s, 1930s, and that's the foundation for all atomic and nuclear weapons, atomic power. Everything related to that came from our understanding of how stars shine. And what happens is when you have that nuclear fusion going on in the inside of a star, and why fusion can occur is because we've got all this mass being pulled down by gravity is creating such a hot temperatures and such high pressure that the atoms themselves get fused together. They get stuck, and that gives off an energy. That energy is what keeps all of this mass from falling in onto itself. When the star is no longer having fusion undergo in the core, it's finished because there isn't this pressure pushing out to keep all this mass from falling in because gravity attracts the fusion energy pushes it back out. This is called hydrostatic pressure from a star. And as long as this is in balance, your star is going to stay alive. And if you're a certain type of star, that if you're on the main sequence, you can live for a very long time. And so what you're looking at here is a diagram that shows you kind of roughly the temperature, and different stars have been labeled different letters. And so down here, the little red dwarf stars, okay? Um, Notice they put Wolf 359 in here. If you ever watch Star Trek, that's where battle for with the Borg happened. It's a tiny red dwarf star. The closest real star to us is Proxima Centauri. It's a very tiny star. And then we got Alpha Centauri, which is further up here. Alpha Centauri. It's much like us. Okay, and so that's our closest real star like the sun, which is 14 light years or so away from us. So you've got these main sequence stars. They live for a very long time. Right? And notice this is our luminosity. So the sun is pretty much average. It's right in the middle. And now then as we move up, notice as we move up, our lifetime of stars shorten. Way down here, these stars don't use their fuel very fast because they're not giving off as much energy. These stars up here, these big blue bright stars, they're using their energy much, much faster. So it's the equivalent of stepping on your gas pedal because you need to get someplace faster. And so you're going to go through your gas faster. And now, as these stars evolve, what happens is they fall off the main sequence, just like us, right? We'll fall off and we'll head into red giant land. These stars head off into supergiants, right? And so when you look up at Alpha Centauri, I mean Orion, you'll see three really bright stars in its belt, and one of those is Betelgeuse. Massive, massive, massive star. You move it down to where the sun is, it would extend all the way out to Jupiter. So it's a really, really big star. Okay? You also have a couple other ones, Rigel, Deneb, also are in Orion. And what happens when those things blow up? You get a massive, massive supernova. So this is what happens to the end of their lives, right? You end up with a blue supergiant. Boom, you blow up. And this is important. These supernovas are the foundation for all life in the universe. Because when they explode, they send out a shock wave. The shock wave can sometimes compress gas and particles and begin to cause the accretion process, which will lead to planet and other star formation. This is why you often see a lot of stars form near nebulas, because the nebulas is what's left over, and it's also compressed all that gas and dust that are out in the universe. That's why you tend to see so many stars around those. Okay? And then down here, you've got the little tiny, tiny, tiny little stars, right? They go forever. And like the sun, we're slowly going to turn into a white dwarf, right? The big blue stars, right? They just go big, bright blue, burn for a long time, and then when they're done, they instantly blow into a supernova. It takes some other times for some other stars. So one interesting difference here is a supernova and a type 2 supernova. A type 2 supernova is when a star is big, but not quite big enough just to blow itself to bits. Okay? Is what happens is when fusion stops inside of its core, all the mass goes rushing in and it rebounds off the inner core, and that causes a supernova to explode. Right? Or what also can happen with these guys is the fusion blows off the outer layers more gradually over time, right? And then if you're the right size and you don't blow yourself to bits, you can turn into a black hole. I would rather blow myself up to bits, I think, as a supernova, because at least then you're left over with your little nebulas. So in those stars that go supernova, that's how the universe is restructured to create all of those hydrogens, oxygens, nitrogens. If we didn't have those, we wouldn't have anything else other than hydrogen and helium, because that's what stars would need. Right, so again, remember that we needed stars to be stable for a long time for life. So we would expect to find life anywhere around this kind of yellow part of the main sequence set of stars. Right? And it does turn out that we are all stardust. So see all these little bright stars? These are all new stars that have just ignited fusion inside of their core. And this is remnants of a supernova. And that supernova gave birth to lots and lots of new stars. Now, what we've been doing with our planet hunters is we can begin to look at the iron levels in the stars. That's going to tell us kind of when in the context of age that star was born within the universe. Because if it has more iron in the universe in it, that means it's a newer star to the universe than an older star. And we're finding that as the iron content of a star goes up, we're finding more planets. We're going to talk about why iron is critical to be able to detect that. Part of that goes from the fusion process, is that we know what happens inside of a star. All those hot temperatures and all of the pressure leads to fusion. You start off with hydrogen, then you go to helium, and then you go to carbon, and then you just keep moving up the chain. And we're going to see what happens as we move through this life cycle and what elements are fused inside of the star, right? And so we know that what slowly happens is kind of this process. You get born, you go into middle age, and then you either blow yourself up or you become a senior citizen. All right, so what we're going to focus on here is we're going to primarily focus on these guys up here, because these are the ones that are going to eventually reach where they can fuse iron in their core. The Earth, we're not going to get there. That's why we're going to just turn into a white dwarf, and we'll see where that happens. Okay, so let's pop down into here. So this is what happens inside of one of those really big red giant or blue giant stars. Is every star starts off with helium and hydrogen at its core. The sun is currently fusing helium, and then right outside of that, it's fusing hydrogen, and then a little bit of helium right outside the core. When it burns through all of that hydrogen, it will collapse a little bit, increase the pressure and temperature, and then helium fusion will begin to take off. That releases even more energy, so that's why the outer layers and why the sun begins to turn into a red giant, because that extra energy counteracts gravity. And what will happen is then it will go from hydrogen to helium, then it will start forming some nitrogen and carbons. It will form a little bit of neon along the way. There's some complicated fusion processes that occur. And then it'll eventually end up with oxygen and carbon, and then it will end up with oxygen, magnesium, right? Then it'll hit silicon, and then from silicon and sulfur, it's going to hit iron. Now, iron is an interesting element. Right? So every time that it runs out of fuel, say it runs out of magnesium, then it has to move on to silicon and sulfur. Is what happens with iron is it costs more energy to fuse iron together than you get out. So that's the first time that happens. So now all of a sudden, once you start fusing iron in the core, it's not releasing any energy anymore. And so what happens is this star will rapidly collapse onto itself, and it's so massive. What happens is all that mass falls in, it hits this dense, dense inner core, and it basically rebounds, and that rebound is a supernova. It's an explosion, and it's a massive, massive explosion. Right? So you kind of go through this process and boom, right, you get one of these nice either planetary nebulas, which is when the outer layers are kind of being pushed away, or you go through this big, massive, big star and it blows itself to bits. Right? So one of these two things. Our sun is on this path. That's why we become a little white dwarf, because we'll have some mass left around because most of our layers are just going to end up floating away. Now here's Orion. So Orion is an interesting sequence of stars, and you can see Orion in the south. Okay? And you've probably heard of the Belt of Orion, right? And here's the Orion Nebula, right? It's a major nursery for stars because the star had gone supernova at some point in the past. This star right up here is Betelgeuse. And in fact, if you begin to look at these stars, you'll begin to see that they do look blue, and Betelgeuse will be a little bit red. And over the last few years, Betelgeuse has been dimming, which we suspect that might be because it is starting to reach supernova stage. Granted, it's so far away that we won't know that for another 700-800 years. All right. And so here is carbon. Here's what's going on with our poor Betelgeuse. Is now it's basically been fusing. It's gone through all of its hydrogen. It's gone through all of its helium. It went to carbon, and now it's now fusing magnesium and oxygen together, and it's now hitting this issue of around iron. Now notice what happens as we begin to head down in this fusion category is as you fuse heavier and heavier elements, it takes more energy to get those elements to form, which makes some sense because when you think about the nucleus of iron, think about how many protons are in that nucleus compared to how many protons are in hydrogen, right? You just need more energy to overcome that positive and positive repulsion of that nucleus to fuse them together, right? You just got a lot more positive charges. And once you hit here, take a look at what happens on the next dip, right? It goes down. Every other one of these is that when you fuse the next one, right, you go up when you're fusing boron to boron together, right? Carbon, you take a little bit of dip, but then you end up with oxygen as a part of a complicated process, right? Then when you fuse oxygen, you end up with neon. You're losing a little bit more, but once you hit iron, that's it. The energy rapidly drops off on what you can produce. Right, so kind of give you a sense of how long these stars last. Like Betelgeuse and those great big blue giant stars, they really rapidly run through their fuel. And once you get to the point where you're burning carbon in the center, you're basically done. And then once you hit iron, you've got 1 day of left life in it. So it's all that's left down here is iron. Your supernova is happening the next day. So that's why if you do a spectroscopic analysis and you're beginning to see carbon and heavier elements in your star, you better get out of Dodge because you don't have a lot of time because your star is about to go supernova. Now, notice here's iron. Here's the mass per nuclear particle. Notice that you head down with fusion. Okay, you end up with a minimum at iron. Now this is where fission also comes into play. Notice that when uranium, which is a component of our atomic bombs, is that when fission happens, right, is that you're going to create some energy. And so fusion and fission eventually all end up leading to iron. Right? But again, iron is the critical one. All right, we've already talked about that, but let's look at a pretty picture of a supernova. All right, and so this is the Crab Nebula. It's one of the more famous nebulas. And when you begin to look at what's inside of it, look at all of these little stars when you begin to zoom in, right? When we suspect that this supernova happened in 1054, it was documented by lots of people because when a star goes supernova, it will outshine most galaxies. There's so much energy that is released. And this is the remnants that are left over. And today, we're starting to see some stars being born. Then we got all of these other guys. All right, all of these elements that make up our periodic table basically came from this. Because when the star goes supernova, it fuses and a lot of energy is released, lots of heat, lots of pressure. That's where all of these other stuff is made. And so when we break it down, right? Everything basically had hydrogen and helium to start with, right? And that's basically what our sun is made out of. Then you get some lithium, beryllium, and boron just being made by fusion and interactions with radiation in space. And I don't really have to worry about a lot of those details. But what's interesting is take a look at the percent of elements that are only made through supernovas. Right? Those are all the ones in blue. We don't know how else the universe got those other than big stars blowing themselves to bits. So all of these guys are critical for our current life on planet Earth because this is where we get our lithium ion batteries, our cell phones, all of these rare earth metals, which are kind of in this column here and in here, is what makes all of our basic electronics work. And notice they're all directly related to supernovas, or they were fused together in really large stars, and then when they lost their atmosphere, those elements got launched into the universe. So think about how many phones are on the planet about these rare earth metals. Right? So these are the critical ones. We're going to see why these are so important. This is kind of what they look like. They do kind of look like metals. They're a little softer. Some of them are kind of more like sodium where you can cut and things like that. But they do just look exactly like that. And you can go up to museums and you can see them, right? But some of them are also very rare. And so you only get little tiny bits of them. But here's what we really want to talk about. Rare earth metals are absolutely critical for how your touch interfaces work, for how your electronics work, for how your electric batteries work, for your phone, computer, cars, all of that. Without rare earth metals, we don't know how to make those pieces of equipment. And right now, most of all the rare earth metals are coming from China. So that's where all the mines are currently located for the most part for rare earth metals. The US, we kind of have one that was in Montana, but it didn't have as much. But look at China, right? Almost all the production happens there. So China actually has a bit of a monopoly over this rare earth metal production, which can be problematic if that's where all of our electronic devices need them. Right? And so this is where people basically get their metals. So the U.S., we basically have beryllium. That's it. Canada has cobalt. Cobalt is critical for electrical cars. But look at China. China basically has them all. Japan has indium right now. India has graphite. All right. Part of why China is so deeply interested in Africa is Africa actually has a fair number of rare earth metals, particularly the Democratic Republic of Congo, Central Africa, has a lot of rare earth metals, or so we believe, right, as part of the mining process. So there's a reason why there's so much investment happening in Africa via China. It's a different type of natural resource. So to give you a sense of what's in what, is iPads, right? Have lots of rare earth metal. Even our turbines, right? Particularly neodymium. Neodymium is what makes those super magnets, right? If you ever picked up one of those magnets, we had some in the lab. They're very strong magnets, right? They're also tend to be used in speakers and things like that. High-end speakers use very strong magnets, and it has to be from neodymium because it's a naturally occurring magnetic material. And then if you have an electric car, right, all the batteries basically rely heavily upon rare earth metals. And here's a little element of all the metals that are happening in your cell phone and what they are used for. So this is a really interesting graphic. I've not found one that's been better than this. And the basic manufacture of these things have not changed at all, primarily because you need the screen, right, which is that very thin Gorilla Glass. That's a very special chemical process, and it was invented long ago. Corning just never could find an application for it until phones and iPads and things like that came into existence. Notice your battery: lithium, lithium ion, cobalt, and then of course carbon, aluminum, and oxygen. Right, but notice cobalt. And then we begin to look at all the electronics. Look at all of these rare earth metals. You need gallium, antimony, phosphorus, arsenic, silicon, right? That's the whole basics for the chips. You need terbium, because one of the things that terbium allows you to do is that, if you have your phone and it vibrates and things like that, is that it's one of the elements that will resonate really well. And so that's where you have that set to your vibration sensor. So each one of these has a pretty strong purpose in what it is that you're doing. They're also pretty good conductors, which also means they're nice because you can use small amounts of them to create high conductivity within your circuit chips, which is important for a phone. Now, probably rare earth metals is going to be the next century's oil in some ways, because hopefully we'll be shifting mostly to alternative energies. But again, you need rare earth metals for turbines. And recently, in 2017, Japan announced a massive finding of rare earth metals off the coast of Japan. Right? And there's a reason why China, right, has been building islands in the South China Sea. There's a suspicion that underneath the ocean floor in this area of the Pacific, there are a lot of rare earth metals to access. The problem is, right, is they're deep down in the ocean, so they're not the easiest to get. Okay. We did recently find a new batch around Hawaii. We haven't really evaluated yet how much is there. The Japan one we think is very, very significant, and that's going to have some political ramifications, because who has access to that? Because whoever has access to that basically controls the world's electronics markets. Okay. So what we'll do is what we'll talk about is, are we alone? And we're going to explore something called the Fermi paradox, which is an interesting paradox, because as we've seen throughout, if we are suspect that is life out there in other places, why haven't we found it, right? We've been on the planet for 10,000 years. Nobody's come to visit us. So where is everybody? And that's the basic question that Fermi asked.